So the first speaker today is Nicolas Abatzoglou. He's the director of the Chemical Engineering and Biotechnology Engineering Department at the University of Sherbrooke. Nicolas is a holder of the Pfizer Chair in Pharmaceutical Engineering. He's also a Theme 1 leader in the network, which deals with fuel processing for solid oxide fuel cells. The title of his talk today is Novel Materials for Fuel Reforming, H2S Removal, and CO2 Capture.
Thank you, Tony. So good morning, ladies and gentlemen. As Tony explained before, what we will present today is the highlights of the research work which has been done, in that case in my labs. And this means that not all of the research work and results which have been produced are presented here, only the ones which might be represent a higher interest eventually for commercialization. So this work has been done at the University of Sherbrooke, and I mentioned as collaborators Partha Sarkar and Tom Etchell from Alberta Innovates Technology Features. As you will see when we have developed the catalyst, so they have contributed in finding how this catalyst can be coated in some types of geometries. I will not present this, perhaps will be presented later by them. So in terms of HUP, not all names appear there, but essentially the students, master, PhD, and trainees, 4 of them are here. Clémence Fauté-Lefebvre has been working for her master degree for the development of the catalyst I will present, and also actually is working for her PhD, not yet finished, on the doped carbon nanofilaments for sulfides adsorption. Ines, who is not with us for family reasons, who actually finishing her PhD work on optimizing the catalyst. Kadayan Samunga Priya was a PDF and left in 2011, and Jasmine, who is with us, have been working on alkane thiols and disulfides doping on metallic nickel, and also defining metallic nickel surface chemistry after its use as a reforming catalyst. Carmina Reyes Plastencia, who is with us, developing catalyst based on doped carbon nanofilaments for diesel reforming. 2 technicians work with us, Henri and Jacques, and trainees. So one representative of these trainees is with us, Marion Meneghetti. And Tony has been a collaboration with other themes. So the background regarding the target of the SOFC was to develop novel steam reforming catalyst. The reason of the focus of the network on diesel is because diesel has a very good drop in fuel characteristics, and also it's not widely commercialized conversion to syngas diesel, conversion to syngas technologies. There are only in-house technologies developed by refineries which are not essentially publicized or documented at the scientific literature, as well as other components like methane. And there is some scientific literature which will be summarized. So steam reforming reminder, I will go fast on this. We have hydrocarbons and water, high temperature and catalyst, and we produce a mixture of synthesis gas, which is essentially the hydrogen and CO. The main reaction is this one, and there are side reactions, desired and undesired. The water gas shift, which essentially is desired when we want to decrease the amount of CO and increase the amount of hydrogen, used mainly for other types of SOFCs or of fuel cells. In the case of SOFC, it's not so important. Methanation reaction, the reaction which is converting CO and hydrogen to methane is undesired, the reverse is desired, and the disproportionation, which is also undesired because it produces carbon which is deposited at the surface of the catalyst and poison the catalyst. So the rationale why liquid fuel steam reforming, we have hydrogen volume density, we have safe storage and existing installations. So having technologies which are able to convert this type of liquid hydrocarbons into energy carriers for SOFC is the target. So why we need a new catalyst? Are the catalysts available in the literature appropriate for this? The answer is not, for different reasons. For example, we have a catalyst like that which has big surface. If we see it closely, we see that after use we have some sintering. This sintering means that we have decrease of the surface, of the available surface of the catalyst. If we go further, we do a reaction which is not at the with the appropriate catalyst and the appropriate conditions, we have this type of image, which if we go closer, we see this black stuff which is deposited at the surface of the catalyst and deactivates this carbon, amorphous carbon or carbon, pyrolytic carbon deposited. Also, other type of carbon which is deposited at the catalyst is filamentous form, like this one. Also decreases the poisons the catalyst, not as much as the pyrolytic, but is definitely something which is hindering the process of reforming. So if we go to the literature review and we make a wrap up, we see that we have three types of catalysts: nickel-based, metals of the 8th group of the periodic table of elements, and non-metallic catalysts. The nickel-based are essentially ceramic supported, alkali promoted, or alloys with copper and silver. I will not go in details for all this, but what I can say that the ceramic supported are the ones which are commercialized mainly using alumina, but more and more is known that yttria stabilized zirconia or nano zirconia is one support which is of very, very high importance for the reasons I will explain later. Alkali promoted were used and are commercially available for decreasing the amount of carbon. However, the alkalis at high temperature devolatilizes and the catalyst loses its activity, but at the same time we have deposition of alkalis in other places of the system. And the alloys which have been used have lower efficiency. The other metals which are essentially tried and with success are the noble metals. Very expensive, at the same time poisoning due to heteroatoms like sulfur is not hindered by this type of metals. And the non-metallic, that is ceria can be pure as it is, can be a catalyst, but the activity is 2 orders of magnitude lower. And the carbides, which are very efficient but are high pressures. If we have no higher pressures, then the carbides loses their consistency and they break down. So in our work, so I will not go in details, but I will explain how we have worked on this. The decision was taken to work with spinels. The moment where all in the literature indicated that spinel is not a good phase to make a catalysis. Spinel is instead a nuisance for the catalyst. We decided to check the spinel efficiency, and we have prepared this on gamma alumina and yttria stabilized zirconia support. The production was made easily and conventionally through wet impregnation. Decomposition of nitrates and formation of the spinel phase at 6 hours at 900 degrees, and has been used in powder form in quartz wool. This is the configuration of the reactor. It's a packed bed, very simple. Hydrocarbons and water are mixed at liquid state using a surfactant at the appropriate ratio. And we have used argon for 3 reasons: as an energy provider to disperse the liquid phase, as an internal standard for the analysis, but at the same time as a means of controlling the gas hourly space velocity. Then, very important thing, water surplus is a nuisance for every type of reforming. In the industry, they use ratios between 3 and 4. In SOFCs, we can use the same ratio, but the energetic efficiency of the apparatus decreases. So the target was to use ratios as low as possible, and all what you will see has been done at ratios lower than 2. I remind that for the stoichiometric ratio for the reforming reaction is 1. and then 2 is the minimum we can accept in the industry, but 3 and 4 are used in order to provide a lifespan of the catalyst of more than typically 1,000 hours. So this has been tested. The catalyst has been done with hexadecane as a surrogate of the diesel with very good results. Then we switched to commercial diesel, and we have obtained a very, very good results at very low temperatures and relatively acceptable gas hourly space velocities. This means typically less than 1 second residence time of the reactive gas. I will not show you other results, but I can tell you that at 750, 760, the conversion of the diesel, which is commercial diesel containing typically sulfur lower than 15, between 10 and 15 ppm, and we can obtain 100% conversion of diesel. And if we compare with equilibrium, we see the different points representing hydrogen, CO, CO2, and methane. We are falling exactly at the equilibrium conditions, which means that the gas hourly space velocity used for this type of reactions is appropriately high, is sufficiently high to get equilibrium. So if we test the catalyst before and after, we can clearly see that there is no nickel, there is no nickel oxide, there is only spinel phase deposited on alumina and zirconia. You see that there are 2 types of zirconias. This is a big, big topic. Is the continuation of my works are essentially there. The zirconias which are sold in the market containing yttria, stabilized for stabilizing the zirconia, are containing a lot of phases, and nobody has searched thoroughly this field. And I believe, after having done a lot of work on this, that this is a big, big area of research in order to improve the catalysts, not only in that case, but in other cases. So if we compare what the catalyst provides us with a catalyst which is a nickel, a metallic nickel deposited on an alumina, and zirconia, exactly the same thing. We clearly see that the initial nickel, metallic nickel, gives a very high efficiency, then it drops fast because we have formation of carbon, while the spinel catalyst is very efficient and provides a stability over about 15 hours. And if we go to scanning electron microscopy coupled with EDX, we clearly see that there is carbon filamentous carbon formed on the nickel, not in the spinel, and clearly see that the carbon signal, which is inexistent in the case of the spinel. So very new results, not belonging to this network because have been done after the end of the network. We have done some work testing the catalyst at 850 gas hourly space velocity is almost double, and using argon as a tracer for dry reforming of methane, which is even more difficult to reform than diesel. And the results stand for about 450 hours. And the catalysts show a very amazing stability over time. The peaks you see here are due to the electricity problems. We had some stops, and when we restarted the reaction, we have got back the initial efficiency. So this is a very important result for the commercialization of the catalyst. So the second thing we are actually have started developing and now is continuing is to use carbon nanofilaments, metal functionalized, for the hydrogen sulfide removal from gaseous fuels. Why? Actual getters are not efficient at low T. You know, people in the industry, they know that. We have to go over typically 500 degrees. The very high T temperatures are necessary to ensure acceptable rates, which are affecting process volume and residence time. And adsorbent regeneration is a big issue, not easy all the times. So in the case of solid oxide fuel cells, let's say that we have a catalyst which is converting the diesel, the low sulfur diesel, with water, the catalyst I have shown you before. Then we have to purify this before getting to the SOFC, because the existence of sulfur, even at small quantities, typically higher than 2 ppm, are detrimental to the anode and the other components of the fuel cell. So we are working in this area. So how we do that? Production of carbon nanofilaments in-house using also a patented process through ethanol dry reforming. Then the carbon nanofilaments are functionalized by acid treatment to introduce oxygen anthers and then make metal impregnation. And finally, the adsorption studies. So essentially, this is the PhD theme topic of Clémence. Methodology shows here. This is the equipment we use. It's a commercial one. We're starting with hydrogen sulfide at 500 ppm and a flow of 30 milliliters per minute. These are typical pictures of transmission electron microscopy pictures for iron and zinc loaded carbon nanofilaments. And I have no time to show you all the results, but I will show you how it compares with commercial systems. We have found these results in the literature, and actually we have ordered some of these commercial to do the same thing in-house. So these are results we have got with our system at a temperature of 300 degrees. If we want to have a gas starting at 500 ppm and have at the exit lower than 1.5 ppm, which is, let's say, the acceptable level for being able to feed its SOFC appropriately, we have a capacity which is between 30 and 40 grams of sulfur per 100 grams. So it's a percentage of the sulfur which is can be got by the adsorbent. And this is what happens in the literature to have with zinc, iron, and titanium oxides. We have to go between 500 and 700 to get concentration at the exit 1 to 10, and the capacity, the retention capacity is between 15 and 40. And with other zinc and titanium oxides found in the literature, at these temperatures, they don't mention this. They mention, however, that the fresh catalysts have a retention capacity of typically lower than 20 and can be regenerated, and after 17 cycles loses about 30% to 10 to 20% of its capacity. So actually this has been presented to the Patents Committee of the University of Sherbrooke and has been accepted for filing a patent, which is ongoing. And the final thing I would like to talk to you a little bit is the greenhouse effect gas sequestration process with some simultaneous production of carbon nanofilaments. We call this process dry reforming induced valorization of environmentally friendly energy carriers. The rationale essentially is not to do dry reforming, but to do sequestration coupled with reforming to have multiple streams of products. So what is this exactly? We have steam reforming produce synthesis gas. This synthesis gas can produce hydrogen, can be raw feedstock for industry, can go to commercial products or as an energy vector, for example, for fuel cells. If we add drive, we can get synthesis gas. But at the same time, we can get the drive through renewable resources or dry reforming from different renewable resources. This not only produces the hydrogen and does also carbon sequestration as an inert powder, which can be valorized. And valorization is done through the work I have presented. And this sequestered carbon is refractory, cannot be oxidized. And if we don't burn it at very, very severe conditions, then is withdrawn from the biosphere, then decreasing the emissions. If we couple this to SOFC, we obtain this type of diagram. We have a fuel in the process, which is the reactor doing the dry reforming. This fuel is fed with CO2 and unreacted fuel, which comes from the outlet of an SOFC. In the outlet of this process, we get CO2 reformed fuel, which is feeding the SOFC to produce electricity, along, of course, by reacting with air. So this makes, if we do the thermodynamics, we can see that about half, this is the reaction. If we do the thermodynamics, we see that if we operate the reactor at 550, we can approximately get 50% of the carbon containing the CO2 as a solid carbon which can be removed from the system. So these are the carbon nanofilaments which are obtained through this process. The white spots you see here are essentially the iron carbides which are at the top of the nanofilaments. This is a nanograph explaining, showing details of the nanofilament. And we have used this type of nanofilaments only as catalysts. So ethanol cracking and dry reforming tests have been done using the nanofilaments produced in the various steps. These, for example, are additional carbon nanofilaments produced and we call them second generation because is the nanofilaments obtained when we are using the nanofilaments as catalysts. And this clearly shows through the XRD that the catalyst is acting, the nanofilaments are acting as catalyst, and as we go to the additional generations, the amount of iron which is contained in the nanofilament decreases, and logically we have additional carbon which is obtained for less carbon or less iron. Then if we get data on turnover frequencies, which essentially is the means of obtaining the efficiency of the catalyst for the production of hydrogen and the production of CO, we see that as we move forward to the next generation catalyst, the turnover frequency increases. This is something we didn't really explain yet, but perhaps it's a question of availability of the iron carbides, which is higher due to higher surface. So I will stop here. I'm within time, I suppose. So I would like to acknowledge the contribution of some colleagues of ours. Nadi Brady, who is a professor at the University of Sherbrooke, not belonging to the SOFC, but has contributed in working with transmission electron microscopy, is a material scientist who is actually helping us to interpret the data obtained through surface analysis. The technical support of these people at the University of Sherbrooke, and definitely the organisms funding this work, SOFC Canada and the NSERC. So thank you very much for your attention, and of course it's open for questions. Thank you very much.
So please, yes, questions.
You know, one of the major challenges in dry reforming catalysis is the long-term stability of the catalyst, particularly for nickel system. You showed about 500 minutes of data on your nickel spinel system. I was just wondering what kind of a stability test information you have for longer term, at least 200 hours of data. Do you feel that it would be optimum to do that in that particular system? That any industry would like to know what kind of a stability test information other than...
In fact, the first years we had no the way of doing these things, so we had limited the duration of these tests up to about 15 hours. But lately we have tried to arrange the lab in order to get more data. We are not perfectly equipped yet, but as you have seen for the dry reforming of methane experiments, we have been able to go up to 450 hours of operation, and we can't go further than that. For the diesel, we have to make some adjustments, but this is possible too. And essentially in the next steps of this work, which are within the new network, the biofuel net, I promise to do that with methane, and essentially you know very well in Enerchem, because you are contributing in this, to test the gasification tail gas reforming. So gasification tail gas reforming in that case contains a lot of methane. It's about 60 to 70%, CO and some other light hydrocarbons, C2. And the purpose is to essentially do the same thing up to 1,000 hours with the gasification tail gas. And I think that this is critical for eventually having the industry being interested.
Just one, I mean, generally you're using rich CO2 methane mixture, or it's kind of a stoichiometric mixture you're using?
Yes.
Okay.
In fact, the CO, when a gas is rich in CO, you have to avoid to have the boudoir reaction taking place, and for that you have to go at higher temperatures. That's why we tried temperatures between 900 and 950 for the dry reforming. But in the case of steam reforming, it's a lesser issue, and we can go between 750 and 800 to have efficiencies without getting the catalyst poisoned. And the fact that this catalyst sustains such high temperatures without having a loss of activity is namely due to the fact that the nickel is not as mobile as metallic nickel at the surface of the ceramic. You know perhaps that the Taman temperature for nickel is about half of its melting point. And you know that mobility of nickel even goes down to 300, 400 degrees centigrade. So if you have metallic nickel, even if it's well dispersed, it's rather possible that you have sintering and a loss of surface, and also bigger grains are sites where carbon can be grown in a much easier way. So the formation of a nanometrically dispersed spinel phase at the surface of a ceramic is a guarantee that this can control the activation of the catalyst.
Okay, thank you, and thanks very much, Nicolas, for a very broad presentation. I think we're out of time, and but certainly there will be more time during the day.